Suppose that we are concerned with two independent populations. Now, both of these populations have a known variance. They're independent of one another. And what we really want to know is, well, what's the difference in their means? In order to do so, we might think to calculate a confidence interval for the difference of means. And in this setup, we're going to be able to use the normal sampling distribution that they're going to ultimately have, as well as sort of Z-based confidence intervals in order to work out what is a confidence interval for the differences in these means. So if we wanted to form confidence intervals for the difference in population means, we can make use of our normal sampling distributions as long as we know the values of those variances. If we don't know the values of those variances, we're going to have to turn towards t-based intervals. So what is the sampling distribution that we are thinking about here? Well, by way of notation, suppose that we have x1 through xn being a sample from some population with a mean of mu x and a variance of sigma x squared. Then similarly, we're going to take independently from that, right? So x and y are going to be independent here. So independently, we have y1 up to ym. There I have a population mean of mu y and a variance of sigma y squared. So we have these two independent populations, each with their own mean and variance. Now, as long as n and m are both sufficiently large, or that these populations are normal, either way it's going to work out to be the same, we're going to have that the difference in our sample means here follows a normal distribution with a mean of mu x minus mu y and a variance of sigma x squared plus sigma y squared, each divided by their respective sample size. If we then want to form a confidence interval, we can use the fact that this is a normal distribution to form a z-based confidence interval. So what does that look like? Well, that takes our estimator here, x bar minus y bar, plus or minus the critical value, so z alpha over 2, times by the square root of our variance here, right? So the standard error, sigma x squared over n plus sigma y squared over m. This is a z-based confidence interval. It follows the same format as any z-based confidence interval. Right, so it's going to be arising since we know the normal sampling distribution, and since the variances are known, we can actually make use of that normal sampling distribution. Okay. If we also wanted to form a one-sided or an asymmetric confidence interval, we could do exactly the same thing, where we just modify this procedure to either subtract off the value here if we want the lower bound, or we could add the value here if we wanted an upper bound. So let's take a look at an example of how this all comes together in this setting, right? We have a nursing researcher who wants to compare the effectiveness of two different pain relief medications. So we have medication A and medication B, and we're specifically looking at post-op patients. The researcher knows the population standard deviation for pain scores for both medications, and they know this from previous research. So in the sample, we take n equals 49 patients, they're given A, and they report an average pain score of 3.2. The population standard deviation is 1.5. Well, M equals 64 patients are given B, and they have an average pain score of 2.8. Population standard deviation is 1.2 here. We want to form a 99% confidence interval for the difference in pain scores between these two treatments. And so what do we need to do here? Well, ultimately, we know that our confidence interval is going to be x bar minus y bar. Right, that's our estimator here. Then we take this plus or minus z alpha over 2 times by the standard error, which in our case is going to be the square root of sigma x squared over over n plus sigma y squared over m. And so we need to be able to identify sort of all of these pieces of information here, right? Going through, we see that n is 49. We see that m is 64. We know that x bar, the observed mean here, is 3.2, right? The observed mean in the second population is 2.8. We have that the standard deviation of the first population, and this is a population value, remember, so sigma x is 1.5, where sigma y is 1.2. We're taking alpha equals 0.01, right? Because we have our 0.99, or 1 minus 0.99 for alpha. Okay, and so we have all of this information, we have the formula that we need, and so then all that remains is for us to actually plug in and work out, well, what is the actual result here? So we have n is 49, sigma x is 1.5, x bar is 3.2, m is 64, sigma y is 1.2, y bar is 2.8. alpha is going to be 1 minus 0.99 because we want our 99% confidence interval. And so then z alpha over 2 is z of 0.01 divided by 2, which we can get to be negative 2.58. How do we get that? Well, we can get that using R. So if we want our z critical value, we look at Q norm, right? Q norm of 0.01 divided by 2 is going to end up giving us negative 2.58 here. Okay, so that's all of the information that we need. Thus, plugging into the formula 3.2 minus 2.8 plus or minus the critical value times by the standard error gives us this interval of negative 0.275 up to 1.075. And so this is a 99% confidence interval for the differences in the average pain scores reported by these post-operative patients, depending on whether they were on medication A or medication B. We can look at a second example here, right? And so in this second example, we have a social scientist who's interested in studying family wealth, right? They want to know how family wealth compares across two different regions. So we'll call those regions A and B. And what they're saying is that they know that family wealth in A is larger than family wealth in B, but they want sort of a lower bound on that difference, okay? And so they want to be able to say, well, A minus B is going to be some positive value. We don't really care what the upper bound of that difference is, but we want to be able to estimate what is the lower bound. And so if we think about what they're actually asking for here, they want an interval that's going to look something like A up to infinity. This is going to give the difference between, say, x bar or mu x minus mu y, right? So the difference here, they want to put this into that interval here, okay? And so what they're looking for here is a one-sided confidence interval. Right. From the first region, they sample 100 families, find a average family wealth of 5 million with a known standard deviation of 1.7 million. In the second region, they sample 100 individuals as well. They find an average wealth of 500,000 with a standard deviation of 200,000. Okay. And so this is what they're set up with. They want a 90% one-sided confidence interval here. Okay. And so to recall, how do we get a one-sided confidence interval, right? Well, we know we're looking at the estimator x bar minus y bar. Right? And we just want the lower bound. So what we're going to do is we're going to subtract off z of 1 minus alpha, right? So that's our critical value. Remember, for one-sided confidence intervals, we don't take z of alpha over 2 because we only need one of the tails. And so we take z of 1 minus alpha. We're going to multiply that by our standard error here, which is sigma x squared over n plus sigma y squared over m, right? And then we can plug in sort of all of the values here. If we want to go through and identify what these values are, we know that n is equal to m. They're both equal to 100 in this case. We have x bar is 5 million. We have y bar is 500,000. Sigma x is going to be 1.7 million. So I'll write just out 1.7 million. And sigma y is 200,000. Okay, and so we have all of our information here. In our case, we want a 90% confidence interval, and so alpha is going to be 1 minus 0.9, which gives us 0.1. Okay, and so that's going to give us sort of all of the information that we need in order to solve through this question. So then we can go about plugging in those values into the relevant formula, right? And we will see that we have our n equals m equals 100, x bar is 5 million, y bar is 500,000, sigma x is 1.7 million, sigma y is 200,000, right? We have alpha is 0.1, and because we want a one-sided confidence interval, we can take z 1 minus alpha, which is z of 0.9. This is going to be 1.282. If we want to get this using R, we take Q norm of 0.9, right? Because Q norm is going to give us our Z critical values here. And so that's how we can get that 1.282. The lower bound is thus going to be x bar minus y bar minus Z 1 minus alpha critical value times by our standard error here. Plug in our values and we get that that's going to be about 4.28 million and some change, right? And so then what is the actual confidence interval? Well, we can take the lower bound up to infinity as that confidence interval. And so then in this case, they're saying that the region A, the mean family wealth in region A is $4,280,557 larger than the mean family wealth in B as sort of the lower bound, the 90% lower bound on what that difference is, right? So they can be sort of 90% sure that the differences in family wealth, it's going to be at least 4.28 million. So using the fact that we have normal sampling distributions that emerge in this setting, then we can form normal-based confidence intervals for the differences in these population means, so long as the variances are known. Now, of course, knowing the variances is going to be a fairly strong assumption. That's not always going to hold. And so whenever that doesn't hold, we're going to need to turn to t-based intervals or other procedures in order to estimate the confidence intervals for the differences in population means.